I will summarize in this video the idea of the linear discrimination models, and I'm going to discuss connections to other well-known model architectures. So overall, in linear discrimination models, what you do is you are looking for a hyperplane defined by a weighted combination of the features. So your discriminator has this linear form. In other words, this is a sum of the feature values in your data points weighted by some parameter vector. And you can use that both for regression problems as well as for classification problems. In the case of regression, the prediction is simply going to be this the result of this linear function. And to train the model, you are going to look at a loss function based on the minimum square errors. For classification, the situation is just a little bit different if you have a binary classification or a multi-class classification. So for binary classification, what you do is you take the value of this linear discriminator and you are trying to switch it to a 0-1, to a value in the 0-1 interval, and you do that by applying the sigmoid function. And then you use a threshold, for example, threshold 0.5, and if the value of the sigmoid function is under the threshold, then you interpret that as a prediction that your data point is in class 0 and it's in class 1 otherwise. And for the loss function, you can use, for example, this log loss. For multi-class classification, the situation is very similar. For each one of the k classes, you are essentially training a linear discriminator model with its own parameters, and to distinguish which one of the classes you should offer as a prediction, you are using this idea of a softmax. So you take the exponential with a parameter being the value of the discriminator for class I, and you normalize that with respect to the other exponentials for the other classes. And you simply are going to take, which class gives you the maximum normalized value in this equation. And for the log loss, it's something very similar as in the case of the binary classification. You just use the log loss function. Now, there are a few things that are important to remember. One is that feature normalization is very important in this case, and also regularization is important to prevent overfitting. Just a small extra detail is that when you do multi-class classification, many of the coding libraries available for linear discrimination require that you are changing your data to a one-hot encoding. Now, when it comes to connections to other models, I want to start with this observation that really the decision in linear models is based on a threshold. And whether that threshold is 0.5, which is maybe the most common choice, or at least the choice that normally you start with, the decision is going to be you are in, say for a binary classification, you are in class 0 if you are under the threshold with your linear discriminator, maybe filtered through the sigmoid, and you are going to be on class 1 if you are over the threshold. And the key idea here is that this is very fragile. Points that are very close to the threshold, but on either side of it, are simply going to be thrown to one class or the other one, even though the difference between them in terms of the linear model is very small. And so when you start thinking about it like that, you realize that maybe you could make the model more robust by having a sort of a decision margin. So in other words, you don't want to be just over the threshold or just under the threshold, but you want to be at some distance from the threshold so that you gain some confidence in your prediction. And that very quickly leads to the idea of support vector machines. The other observation I want to make is that you can actually see this linear computation done in linear discrimination models as a sort of a feed-forward computation. And the way you see this, you can, for example, think about your data point, your input, as some sort of a layer. And what I mean by that is that you're going to have some node for each one of the features in your data. So this would be, for example, the first feature, the second feature, and the third feature. And your linear model is going to, calculate some weighted linear combination of these. So you can see this as arrows that feed forward into the computation that the model does. And each one of these arrows is weighted by its own weight. That's going to be, calculated by the model. And this additional free term, you can actually see it in the same way. This is also a linear computation applied to some node where the value is 1. And I'm just writing it here as 1 so that we have a single sort of presentation, so that this part, free term here, is not a special computation. It's just the same thing where this is an extra feature that is always equal to 1 for all the data points. And in the case of multi-class classification, the situation is exactly the same. You have this input layer, all the features in here, plus this extra feature constant to 1. And you have independent computations, independent, decision boundaries, in independent hyperplanes for each one of the classes. So each one of these arrows has its own parameters that are being estimated during the model training. So when you have this, you start seeing this linear model as a sort of a network. You can especially see it as a network on this side. With two layers. You have the input layer here and you have the second layer in here. And you start thinking then that, hey, maybe this could even be combined. Maybe there could be another layer and doing the same sort of computation. And so this leads to the idea that these are, in fact, perceptrons. That's the name that is well established for this sort of architecture. So these are perceptrons that could be maybe combined into multi-layer perceptrons, where you have several layers of similar computations, and that in fact leads very quickly to the idea of fully connected neural networks or deep neural networks.